Hello students, very good afternoon to you. Let me start with the explanation on Euclidean space. So here by Euclid, it is in Unit 5 or Unit 4 of Advanced Calculus 2. So the notes I've already sent to you. So I just want to explain to you what is meant by Euclidean space and some of those basic properties of algebraic operations here. So as far as we know that you have come across the word xy plane and the xyz plane. So the collection of all points here, this is denoted by R to the collection of all points in the two-dimensional plane. This is a two-dimensional plane. It is xy plane. The R2 here is the collection is denoted for the set of all points in a two-dimensional plane, and the collection of all points of the form x1 x2 such that x1 x2 belong to R is called a two-dimensional Euclidean space. Similarly, R3, the collection of all points in a three-dimensional plane, that is ordered pair, a set of n points, 3 points x1 x2 x3, such that each of these belong to the set of real number, is called a three-dimensional Euclidean space. So in general, the collection of all points, an ordered set of n real numbers, say this one x1 x2 dash dash xn, is called an n-dimensional point or a vector, and for this we usually denote it, for this collection of n-dimensional point, we denote it by this vector or point, say x bar, with n components x1 x2 xn, with each of these belong to the set of real numbers. So the collection of all n-dimensional points in a n-dimensional plane is called an n-dimensional Euclidean space, and we usually denoted it by x bar. Points or vectors here, this set of n points, in this case we denote it by x bar, say, which is x1 x2. This also can be denoted as x bar, which is equal to x1 ordered of n 3 points x1 x2 x3, an ordered set of 3 points, 3 real numbers. So in general, the collection of all n-dimensional all points in an n-dimensional plane is denoted by Rn and is called n-dimensional Euclidean space. And the collection of all points, the points on Rn is of this form, ordered of n real numbers x1, x2 dash dash, xn, and each of this point is denoted by this point x bar or x bar, and x1, x2 are called the n components. Now, with this definition, we are going to find some of the algebraic operations in Rn defined as follows. You denote x bar as the collection of n-dimensional real numbers x1, x2, and y bar to be again an n components of real numbers, say y1, y2, yn, each belong to Rn, because Rn is the collection of all such points. Okay, and how we define the sum of these two vectors or 2 points in n-dimensional plane? It is x bar plus, the sum is defined as x bar plus y bar, where you add each of the first component of x bar with the first component of the second vector. Similarly, the second component of this first vector is added to the second component of the second vector, that is x2 plus y2 dash dash. So the sum is defined in this way. Equality, these two vectors x bar and y bar are equal if each xi is equal to yi for all I, means x1 is equal to y1, x2 is equal to y2 dash dash, xn is equal to yn. In the syllabus Rn here, they have mentioned n here, it can be 1, 2 and 3. Okay, so in general I'm giving you the proof. So if they ask you in case of R3, so you denote it by set of ordered 3 real numbers x1, x2, x3, and y bar as y1, y2, y3. If it is if n is equal to 2, if n is equal to 2, then you denote this point vectors as ordered pair x1, x2 and ordered pair y1, y2. So and here I'm doing it in general in case for n, okay, where n can be 1, 2, 3 or any. Now, if for any scalars a, any scalar quantity a, you multiply it with this vector, then it will give you ax1, where you multiply a with each of these n components of x bar, that is ax1, ax2 dash dash, axn. And the difference is defined as the difference of these two vectors is defined as x bar minus y bar equal to x1 minus y1 dash dash comma xn minus yn, which is equal to x bar plus minus y bar, which is same, means you can interchange this as x1 plus minus y1 dash dash and then xn plus minus yn, which can be rewritten as ordered pair x1 x2 dash dash xn plus ordered pair minus y1 comma minus y2 dash dash minus yn, which is same as, you can take minus sign here, ordered pair x1 plus comma x2 dash dash xn minus ordered pair y1 y2 dash dash yn, which gives you nothing but x bar minus y plus of minus vector y bar. And here the zero vector or the origin is denoted by 0 bar is where each of the n components is equal to 0. So 0 vector is set of ordered n components where each component is equal to 0. And inner product here is defined as, the inner product of these two vectors is defined by this notation: x bar dot y bar is equal to summation of xi yi, where I varies from 1 to n. This is a definition, means you have, this is what we have defined there. This is the algebraic operations we define in the set of n Euclidean space. So throughout, by x bar dot y bar we mean summation of xi yi, where I varies from 1 to n. And what is x bar? X bar is nothing but the set of n components, n component real numbers x1 x2 dash dash xn. Similarly with y bar. Norm or length, we define here this norm or length of vectors x bar is defined as this one. This is a notation which is equal to summation of xi squared to the power 1 by 2, or it is equal to square root of summation of xi squared, where I varies from 1 to n. And this norm is also called the distance of this vector x bar from the origin vector, means the origin here stands for the 0 vector. So in case if you have two vectors x bar and y bar belong to Rn, then the norm of x bar minus y bar is nothing but the distance between these two vectors, that is the distance of x bar from the vector y bar, which is denoted by d of x bar y bar, and it is nothing but square root of summation of xi minus yi the whole square. So thus we have d here is a function defined. This distant function is defined as a function defined from R, and the cross product of these two real numbers and Euclidean space Rn cross Rn to R. That is here x bar and y bar, where x bar belong to this first this set and y bar belong to this, such that the d of this x bar y bar is nothing but the distance between these two functions, which is in the form of real number, and it is called a distant function between the distant function in Rn. So in case if you have n is equal to 1, that is in case of real number, the distant function d here is nothing but denoted by mod. Instead of that double notation, we have just mod, that modulus of x minus y, that is the distance between two real numbers x and y, where x and y belong to R. In R2, that is when n is equal to 2, the distance between two vectors x bar and y bar is nothing but square root of summation of x1 minus y1 whole square plus x2 minus y2 the whole square. And here we have some elementary properties using this definition of norm and norm or the distant formula function. We are going to define some elementary properties of distant function d. So for any x bar, that is for any vector which is equal to the set of n real numbers x1 x2 dash xn belong to Rn, norm of x bar, the distance of x bar from the origin is always greater than called 0. Why it is greater than 0? Because it follows straight away from the definition. What is norm here? Norm is equal to summation of xi squared the whole raised to 1 by 2, where each xi here, even if xi is a negative value, but because of the square, it is always greater than or equal to 0. Okay, so that's why the distance of this vector is always greater than equal to 0, because norm here is defined as square root of summation of xi square. So all the term inside this x1 square plus x2 square dash dash, they all become positive numbers. So therefore it is strictly greater than or equal to 0, whereas it is equal to 0 if each of this component x1 is equal to 0, x2 is equal to 0, x3 dash dash xn is equal to 0. And if you have for any a belong to R, a here is a scalar quantity or a real number, then you multiply it with this a bar inside the norm, that is the distance of this x bar. This is same as mod of a into norm of x bar, because for a inside, even if it is inside the norm, if for any a belong to R, we define norm as modulus of, as mod only if for n is equal to 1. So a here is a real number, so therefore norm of a x bar is equal to mod a into norm of x bar, that is summation of a xi square the whole raised to 1 by 2 is equal to mod a into square root of summation of xi square. Similarly, the distance between these two vectors, norm of x bar minus y bar, is same as the distance of y bar minus x bar. You just interchange the plus and minus sign, because what is this norm of x bar minus y bar? It is defined as square root of, as you can see here in this formula, what is this distance of x bar from y bar? It is defined as square root of summation of xi minus yi the whole square. So even if you expand this, xi minus yi the whole square is same as yi minus xi the whole square. So therefore, this is same as square root of summation of yi minus xi the whole square. So the distance of x bar from y bar is same as the distance of y bar from x bar. So I think I'll stop here, because the proof of these three elementary properties, it follows straight away from the definition I have explained to you, whereas the proof of this property D and E, I'll give you in the next video. Okay.